Hey guys, this is the DDP student bringing to you Chapter 9, Relative Permeability. Um, this chapter was really long, so I'm not going to get to everything, and so I'm just going to try to do my best. The general equation for relative permeability is relative permeability, or Kr, is equal to effective permeability over absolute permeability. And then first kind of thing is the fluid saturation for gas and water. As you can kind of see here, you have your equations for the gas and the water for the permeability curves. So I'm not really super sure what those mean, but I mean that's just gonna go with it. But I know that you can kind of use logic, figure that. So at 100% saturation, the relative oil permeability is always 1. And when the base permeability is 1, the gas saturation has to be 0. So if the core sample is 100% filled with oil, then the oil saturation is 1. And if it's 1, then the gas saturation has to be 0. Then we get to measurements for relative permeability, and we use the S. I don't know if it's called SCAL or SCAL, special core analysis. And for this method, you always use the gas oil measurements. Do the gas oil measurements before the oil water measurements. And there's 2 ways to test it. You can either test it at room temperature or reservoir conditions. Room temperature is easier but less accurate. I think we've discussed this before in class, and the reservoir conditions require a lot of time and effort. But pretty much you have the steady state method, or SS, and for that, pretty much starts with 100% water saturation, and that'll lead you will begin adding oil. So we have our water, their oil, and so you get kind of a balance, and then you'll increase the water steadily until you can find your saturation. And then see that the measurement is is the new water saturation is equal to the or this or yeah, it's equal to the mass. I'll just write it out and then explain it. So it's the the oil saturation is equal to the mass of the rock and the fluids subtracted by the mass of the dry rock minus the pore value multiplied by the oil density divided by the pore value multiplied by the water density minus the oil density. And then you can also the steady state method will also give you your effective permeability calculation. Apologize for my handwriting. It's probably worse than Jaden's. And here is the equation for the effective permeability calculation, which is it's just derived from Darcy's law. And there's more to it than this. These are just kind of a summary of the basic equations, but if you want to see how they're derived, it's written in the book. It's just a kind of a lot to go over. So that's a steady state method, and then we have the unsteady state technique. If you can see that. I'm currently filming this. My phone is suspended above my desk with duct tape, so I don't know how well you can see it, but I hope it's satisfactory. And the unsteady state technique is based on the interpretation of the data obtained during an immiscible data process. And it's a way to determine the relative permeability. And the should have written down somewhere where I thought I wrote down some notes about them. All right, well, basically, the unsteady state technique, or the USS, will give you three equations. And they pretty much go from the Buckley Levert to the Welge equation to the Johnson Bosler and then Naumann equations. And then basically you start with Darcy's law, and then you find the capillary pressure, and then use that equation to find the fractional flow. First of all, to find the sum of the variables you'll need to start with your Buckley-Levert equation. And again, I don't really feel like writing all that out, so if you're curious on how that's done, it's in the chapter. So the Buckley-Levert equation tells you the constant rate of water injection and the velocity of a plane of constant water, and it tells you the velocity of a plane of constant water saturation is directly proportional to the derivative of the fractional flow. And then basically that equation will end up being again, you have to derive it, but I'm taking calculus right now, so I still don't really understand how that quite works yet. But it's whatever. Then the Buckley-Levert equation lead to the Welge, which leads to the Johnson-Bosler-Naumann, and the Johnson-Bosler-Naumann method